All right, I was absent yesterday. Obviously, we had a little bit of homework that we had assigned on Tuesday and from yesterday. Today, the first bit was page 569, 467, and 9. And the next was worksheet number 7, questions 3 and 4, worksheet number 8. Any issues with those? Page 569, 4. Any other section 4? 6? Yeah, we can do it. 7, 9. Sorry, number 4 was the first one we moved forward. It says, let's copy this over to the space. It says that a point in Earth's atmosphere, the electric field is 150 coulomb, downward. The gravitational field is 9.80 kilogram downward. What's the electric force on a proton at this point, and what's the gravitational force on a proton at this point? The proton is what? The proton, the producer, or the experiencer. In both cases, A and B, whether we're talking about the electric field or the gravitational field, is it the producer, is it making the field, or is it the experiencer feeling the field? It's the experiencer. So in question A, we've got an electric field experiencer. In question B, we've got a gravitational field experiencer. Now, the electric field experiencer equation is this one. E is equal to F over P. And the gravitational field experiencer equation is G F over M, which is really just F is equal to M times A, right? But A is gravitational field or acceleration of gravity. We're going to rearrange both of these equations to solve for F. In this case, the electric force is equal to Q times the electric field. So we're dealing with a proton with 1.6 times 10 to the minus 1. You don't know what the term of the proton is? That's okay. Where do you find it? On your data sheet, it's 1e. The E is the limiting charge, 1.6. So, proton is going to be 1.6 as well. The electric field strength is 150. You multiply those two together, you should end up getting 2.4 times 10 to the minus 17 newtons. Electric force, 2.4 times 10 to the minus 17 newtons. Now, the force, gravitational force on the proton is going to be found by multiplying the mass times gravitational field. So it's 1.67 times 10 to the minus 27 kilograms times 9.80. Whatever is 9.80 here instead of 9.81. And multiply these two together, we're going to get somewhere in the range of 1.6 times 10 to the minus 6. Not exactly, but that makes sense. Now, which one is the bigger force? The electric force. You probably could have predicted that, right? Because as soon as we started talking about Coulomb's law, way back near the beginning of the series, when the electric force, almost always is going to be bigger than the gravitational force. The gravitational force in the grand scheme of things is a weak force. And we can see here that it's kind of a 9 times bigger electric force than the gravitational force. Right? All right, let's take a look at question number 6 now. It says, what is the electric field intensity? So we're only looking for the magnitude here, the intensity, as opposed to the direction. 0.3 meters away from a small sphere, and the charge of 1.6 times 10 to the 8. Is this charge here? It's something that you want. Is that a producer or is that an experiencer? Is it making the field 0.3 meters away, or is it feeling the field? It's kind of unique. Let me have a little analogy. Okay? 100 kilometers above the surface of the Earth is a certain gravitational field. You agree with that? It's going to be a little bit less than 9.81, right? But it's still going to be a gravitational field there. Now, we're given information about the Earth. The Earth is clearly the producer of that gravitational field, right? When you're trying to find the field strength a certain distance away from a charge, well, that charge is going to be a producer. It's just the same as when we're trying to find the gravitational field strength 100 kilometers away from the surface of the Earth. The Earth is a producer. where the charge is, and that charge is going to be experienced. You don't experience something if you're not there. We're trying to find the field strength 0.3 meters away from it. Well, we can experience it. That charge is there. It's got to be the producer. Given the fact that it's a producer, we're going to use the equation KQ over R squared. One long-term piece of it recognize like this, right? K times 1.6 times 10 to the minus 6 divided by 0.3 squared. Not sure we'll get there. Pretty straightforward if you recognize that it's a producer as opposed to an experience. What are the units that I could have used there besides units before? Is there anyone that we wouldn't want to do today? Let's repeat that. Although typically with that equation, you see units are wrong, but ultimately that's the balance, so you put that out and that's it. Okay, question number 7, what's a little bit easier question of 6. 7 says, calculate the electrical intensity equating to two negative charges, 3.2 microcoulombs and 6.4 microcoulombs. Separated by 1.4 meters. So a lot of your charge 1, your charge 2, this guy is 3.2 times 10 to the minus 6 coulombs, 6.4 times 10 to the minus 6 coulombs. And it's going to be 0.20 meters. Midpoint, 0.20 meters away from each of those charges. They're both negative, right? So let's draw the directions here, okay? We've got a field caused by number 1 that points to the left, points towards the negative. Field caused by number 2 points to the right, points toward the negative. We've got both of those directions. Now let's get the values. Q1 is going to be K1 over R squared. It's 0.99 times 9 times 3.2 times 6. Divided by the square is 0.20. The value of that? Or, as we saw Tuesday, could be both swings as well. The second one, I don't know if anybody saw this. E2 is a short microphone in that one. This is going to be 1.438 instead of 6 meters per coulomb. Now that that one's a quick. The distance is the same. The charge is double. So I effectively in my head variable value change. Right? Now, why was I able to do variable value change in my head? Because it was so complicated squaring or anything like that. It was doubling the charge. 2.264. You didn't slot that. That's okay. Just do the computation. Better. Now we're going to add these up. Q1 is negative 7.19 instead of 5. Which is positive 1.4 times 6. So that goes out. We're going to say positive 7.19. Good. Again. All right. And note 7. Okay. And the last question we had was question number 9, which is pretty similar to 7, except you do the one other side. We want to find the magnitude and direction of the electric field at point P this time to the right of both of those directions. We've got the microcoulombs, we've got meters, 9 centimeters. It's like a little easier for us. Draw our diagram here. The field caused by number 1 is to the right, that's it's a bit of a positive. The field caused by number 2 is to the left, it points toward that negative. The values of both of those fields. C1 KQ1 over R squared. Q wants 50 times 10 to the minus 6. Don't put the exponent there. Circle that helps you do that. And this is 0.45 meters. It's both of those distances you can see in the diagram. Square, right? Added together in the square. What do we get for you on that? 2.22 times 10 to the 6. Four whole through here. E2, a little bit easier. Same method. A little bit easier to solve it. Add those distances together. Now it's easy, right? We have a diagram going which shows the direction. We have the values calculated. We know the direction, we know the values, just add them up. 1 is going to be positive 6 plus E2 is negative 4.00 times 26. We add those up, we should get 1.7 times 26. It's a positive value. It's a positive value. Okay? All right, everyone, see all the answers to worksheet number 7 here. We have to get 4 of these instead of 1 and 2. These are any of those questions. 7. Once, twice, so these are all good. That's I would see the answer to question number 8. Up on the board now. Choose question number 8. Oh. 4, 5, and 9. Yes. The others. 4, 5, 8, 9. Okay, we can do that. All right, let's take a look at question number 4, 5, 8, 9. First question number 4 on worksheet number 8. It says calculate the distance from a 3 coulomb charge to the negative field strength is 1.09. So looking for the distance, we've got a value of charge here. It's 3 coulombs. And we're getting the situation. By the way, is that charge a producer or an experience? Trying to find the field strength certain, so we're trying to find the distance away from the charge. Is that value? Is that charge a producer or experience? It's a producer, right? Trying to find the field strength a certain distance away. Gravity producer, not you can't experience something if you're not there. The charge isn't at this spot, so it can't be an experience. That's the producer. So let's just take the equation. KQ over R squared. And solve for R. The R squared is going to multiply. Q is down to divide. And how do we produce squared? So we're doing right. So R is equal to square root of KQ over E. It's a number of 84,929 times 3 divided by 1.09 times 10 to the 11. And the square root of the calculator. And the square root of all of that, and you should get 0.197. You want to see that? Oh, was that okay? Was it a pretty switch experience as well? Oh, okay. That was you know. Let's put the numbers in before I so we get 8.9 times 3 divided by 1.09 and 11. And then get square root of that. Pull up here. Let's say 8.99 times 9. Multiply that by 3. Divide that by 1.09 times 11. You should get all the exponents, so it's easy to make an exponent. Although that would right, let's see what the first number 6 says. 6 says, calculate the experience of an alpha particle. The alpha particle is the experience of gravity. And then force experience is 2.0 times 10 to the 16 meters. And what's the acceleration? So we want to find electrical experience. We know that the charge of the alpha particle is 3.0 times 10 to the 19 from the data sheet. And that's the alpha particle. That's on the data sheet. And we know that the force experience is 2.00. The experience of physics, what's the field experienced by the alpha particle? Experience of the wave. It's 2.00 times 10 to the 16 meters divided by 3.20. Now, that not getting 6.25 to 2. Now, when I want to go find the acceleration, our instinct is to say, oh, I'm probably use the answer that we just got. But we don't. We already have force. So let's just say n is equal to the force that we were given in the question divided by the mass. There was 3.0. Can I stay a little longer? The fastest speed we possibly have is v times 10 to the 8 per second. This is what's possible. That will be possible. Good. Acceleration. There's no upper limit to acceleration. You have acceleration velocity used, but they're not the same thing. It just means that it's going to accelerate to a rate that's really going to be close to the speed of light. Maybe it'll be really quick. But it's still not going to ever go over 3.10 meters. All right, next question, number 7. This was describing the net force experienced by an electron. The field experience is 1.0. Experience. Force experienced by an electron. And they give you that word, come on. They give you that word experience, you know it's experience. You know the charge is negative 1.6 times 10 to the 17 well, we can drop that. The field is 1.00 times 10 to the 3. Yep. Wow. All right. So we look at number 5 then, I guess, because that's the one you actually asked for. Okay, let's look at number 5, 8, 9. You did number 4, right? Okay, let's look at number 5. 5 says, what's the electric field experienced by an electron? Same logic in this question, right? If we got the word experience and we know it's an experience, the electric field experienced by the electron charge is negative 1.60 times 10 to the 19 coulombs. And the force experienced is 2.00 times 10 to the 16 meters. I'm going to say easy to that. You don't send the data sheet. You don't have the absolute value set or the experience equation. That made up the data sheet. I'd put it on there. I'd put the absolute value set. In fact, sometimes you see me when I write down the equation, I do that anyways, even though it's not the way it's written in the data sheet. The reality is that equation on the data sheet isn't going to get us direction. It's a vector. It's not going to get us direction. So by rights, we should have the absolute value set. Zero times 10 to the 16 meters. By the way, the charge is 1.60 charge, as we always do. We end up getting 4.06 centimeters. Okay. Well, this is easy, right? 2.5 centimeters from both of those charges. And we have a charge of 5.00 and 2.50. Now, one of the areas I think where some of you made mistakes in this question was the field direction. The way you start one is to away from the ball. It is toward charge 2 because charge 2 is negative. It always goes towards it. We're going to calculate the value of both of these fields now. I'm not sure that we need to actually do that. You guys should find one. We do that. We get a value of 8.879. Calculate the same method here. You get 4.44. Now, we're going to add these up, but the temptation, right, is to say, well, we got a positive charge and a negative charge. One of them is going to be a positive field, one of them is going to be a negative field. But that's not how we decide whether to be positive or negative. We decide whether the positive or negative based on the direction of the field. And they're both, in this case, to the right. We're going to be more positive. To add them up, we're going to do that. Positive values. Good question. I've never seen this before. It's the same thing, right? Just got three charges instead of two. There's no difference in the method. It's just a little bit longer. All right. Final question number 9. Since three charges are this very low, your charge 1, your charge 2, your charge 3. 2.50 times 10 to the negative 2 coulombs, negative 4.00 and we've got 3.00 and 10 to the negative 2 coulombs. We're trying to find the fields right down here somewhere. Point X. This is 60 millimeters. This is 5 centimeters. Centimeters in the same question. That would be easy as a mistake on that. It's so easy. Especially important to certain units. This one, because not only are they not standard, but they're different as well. All right, let's get our directions here. Field conjugate number 1 is to the right, because it's away from the positive. Field conjugate number 2 is to the left, it's toward the negative. Field conjugate number 3 is also to the right, because it's away from the positive charge. So we got our three field directions here. We got to get our values of these fields. Then we got to add them up. Negative value. You know what K is? You know what Q1 is? 2.5 times 10 to the negative 2. Let's argue. Do that again. Quickly put in the meters and do that. 2 centimeters is 0.02 meters. 5 is 0.05 meters. 60 millimeters is 0.06 meters. We add those up and we get 0.1 meters. If you get a value for E1, you get 1.299. We're going to find it the same way. We know what the value of Q2 is for common centimeter. It's 4 minutes. R this time is going to be 0.07. We do the math there. 7.3388. And then finally, charge 3 produces a field at point X based on the distance you add those up, but when we add them up, you got to make sure that this one is a negative value because of the negative charge. Because the direction is to the left. You add those up, and it should be that it's a 80 or 6.1. Okay. I want to take a look at two multiple choice questions here. Um, they're both based on this information. We have the automotive one and the spark plug. Two questions are in multiple choice number 47, and the numerical response number 48. Now, I'm going to give you a little bit of context to this. You need to know that the concept of transformers needs to be a part of the system. Now it's not. You don't need to know anything that the say. Now, we can still answer this question, but if this is a question that's given today on the diploma exam versus what it actually was on the diploma exam, they would give you a little bit more information. They might give you a transformer question, but then explain it a little bit better, as opposed to just kind of assuming you knew the transformer. The important part here, you recognize that you use something in the transformers, is that when we're talking about the secondary coil here, spark plugs, in this question 47, we're talking about the secondary coil. Spark plug is in the secondary coil. In the secondary coil, it tells us the potential difference from voltage of 40,000 volts in the secondary coil. We're doing two different differences here, 12 volts and 20,000 volts. If you want the one in the secondary coil, that's where the spark plug is. Does that make sense? Again, had you taken this course 5 or 6 years ago, you would know that. You would know that yourself. Because we'd be looking at transformers and understanding. All right. So knowing that, let's take a look at those two questions, 47 and 48. Don't bother submitting these because I'm not sure that you have time to do that. These questions let's take a look at 47 and 48 here now. 47 says, what's the strength of the electric field induced in the gap of the spark plug? Look, in question number 47, we want to put the electric field strength induced in this gap of the spark plug. We've got a potential difference here of 20,000 volts in the secondary coil. If we get a distance between the gap, or the distance of the gap of 2.01 meters, or 2.0 times 10 to the minus 3 meters, it's just logical that we're going to say E is equal to delta V over delta T. Now, somebody might say, how do we know that it's a uniform electric field? Doing like that, because it's, they're really like two parallel plates, they're pretty small plates, they're parallel plates. Well, here's the thing. Very, very local on this area. The electric field is always in there. It's just over a bigger area that sometimes not uniform. We take a look at two charges right here. It generates an electric field that looks something like this. Okay? Take a look at the spark plug gap. Here's the top of the spark plug. Here's the bottom of the spark plug. Okay? It's not quite 2-point charges. Are we going to get all of this stuff over here? Yeah, probably not. But if two parallel plates, you get the exact same thing. The edges that are non-uniform, we call edge effects. But right between those parallel plates, it's a uniform field. As small as these parallel plates may be, over that very, very localized area, it's a uniform field, which means we can use the equation E is equal to delta 20,000 volts divided by 2.0 times 10 which is split at 1 times 7 volts per meter, or 1 times 7 times so now we want to find the acceleration of electrons. We would say A is equal to F over M. But to get the force, we need to use the experience report that we use. So 1.6 times 10 times around 5 and a half, I'm going to give it to your data sheet. That way. Now, look at the way they want this one. It's on B, transfer to CD. It's A, B, C, D. What's the answer? Okay. Very good.